I'm Ed Stone, the chief scientist for the Voyager mission, which flew by Jupiter, Saturn, Uranus, and Neptune, and is now in interstellar space, the space between the stars. For me, this has been a personal journey of discovery for over 42 years, and I hope that it has inspired you for your own journey and your life ahead. I'm trying to understand the universe, and that means exploring, observing it in new ways, and putting together the pieces of the puzzle that tell us that, for instance, that the universe began in the Big Bang 13.7 billion years ago. It's understanding how that Big Bang resulted in what's around us today. Voyager was the first automated spacecraft, so in that sense it's affected all the design of all the subsequent missions, because it was the first which had computers so it could maintain its attitude and control, but it also could sense when something was wrong and take action to switch to backup systems or make other corrections. So that heritage now is in all of the rovers on Mars and all the other spacecraft we fly. There was a CALTECH graduate student working at the Jet Propulsion Laboratory on a summer job in 1965. His job was to look for opportunities to fly by a planet and allow the planet to sort of slingshot Voyager or a spacecraft further on. And what he discovered is that the 4 giant outer planets all end up lined up in such a way that a single spacecraft can fly by all 4 in a period of about 12 years. It was called the Grand Tour. But you had to launch in 1977. The last time this opportunity was there, Thomas Jefferson was the president. And the next time will be the next century, the 22nd century. The 2 Voyagers were based on what were called the Mariner spacecraft, which flew by Venus and Mars. So they were spacecraft designed for near the Earth. The idea was to build on that for a mission that could get to 10 times as far from the Sun as the Earth, where Saturn is. So it has a large antenna, 12 feet in diameter. That has to always point at the Earth so that it can send back the data. It has on it a power source, which is just the heat from the natural radioactive decay of plutonium-238. The 2 Voyagers were built identically because we did not know how long they would last, and we had to guarantee with some high probability that at least one would survive a 4-year mission to Saturn. Well, of course, both have survived. Both went by Jupiter and Saturn. Voyager 2 went on to Uranus and Neptune. Voyager 1 now is the furthest out and is the first actually to reach interstellar space. Voyager 2 will be there in maybe the next several years. That's what we will find out.
Can you talk a little bit about what computers were like in 1977 when you sent Voyager on the mission, and how much things have changed and how that's played into your discovery of information now?
We, of course, have very old computers on Voyager, and we continually adapt them when we have to, but we're very limited by the computers. On the ground, of course, we've upgraded over years, and now what you could do on a desktop, what used to take a room-sized computer. So now it's much easier to do the downlink analysis work than it was, say, 20 or 30 years ago. Voyager was designed for a 4-year mission to Saturn. Saturn is 10 times as far from the Sun as the Earth is. And now we were going to go on to Uranus, which is 19 times as far from the Sun, and then eventually Neptune, which is 30 times as far from the Sun. So there's much less sunlight out there. That means you take longer exposures to take images. And of course, the radio signal coming back is 9 times fainter than it is from Saturn. So we had to both change the software on the spacecraft to make better use of the limited capability of sending back the data, and we had to enlarge our antennas here on the Earth to collect these weak signals. But we did all that so that, in fact, we could get images back from Neptune in 1989 at a distance 30 times as far from the Sun as the Earth. We had to design Voyager very carefully because the radiation environment at Jupiter is terrible. It's very, very damaging. So we had to choose electronic parts very carefully so they would not age too much. We had to design the circuits so that even if the parts aged, the circuits would continue to work. And then we had to add shielding to protect the parts from the particles. Fortunately, that all worked very well. We had only a minimal amount of damage when we flew by Jupiter. That was by far the worst exposure that we had, and that's part of the reason the spacecraft are so long-lived, is because we had to prepare them to survive Jupiter.
Pope Francis talked about the importance of looking at the world from the outside in, as opposed to being concentric. How do you think Voyager has changed our view of the Earth and our place in the cosmos, both geographically and as human beings?
Science is about learning something you didn't know, and so what you look for is to see things you hadn't expected to see. Those are the most important surprises, because that means there was something you really didn't know was there to be discovered. And Voyager, time after time, had such discoveries. One thing we learned from Voyager is how limited our Terra-centric view is, not only of Earth, but of everything in the solar system. Before Voyager, the only known active volcanoes were here on Earth. And then we flew by a small moon of Jupiter called Io with 10 times the volcanic activity, 8 active plumes. It was just remarkable. Before Voyager, the only known oceans were right here on Earth. And then we flew by Jupiter's moon in Europa and found that it was an icy crust, probably on the liquid water ocean on that small moon. Just time after time, our Terra-centric view, based on being here on Earth, was just much too limited in terms of what's really out there, and also too limited in our understanding of the Earth itself. Some of the earthquakes on the other planets are actually earthquakes in water ice. That is, the rock is not really silicate rock, it's water ice, which is so cold it's as hard as rock. And so you have different processes, different results of earthquakes and tectonic processes on these other bodies. But they're related, but they differ in detail. The processes are related in the sense they involve heat, which is in fact stressing and cracking the surface. For instance, the volcanoes on Io are not like the volcanoes on Earth. They have plumes which are 100-mile high. We have no volcanoes on the Earth with plumes 100 miles high. So yes, they're volcanoes, but they're not like the Earth in detail. What Voyager's done is it's revealed how the same processes that have shaped Earth have created quite different objects in the solar system. And that means we can come back and look at the Earth again to be sure that we really do understand how the Earth evolved to what it is, and even perhaps more importantly, try to understand what the ultimate evolution of the Earth is going to be.
Is it still possible to remain open to the new and unexpected, and has the unexpected been a resource for you?
The unexpected really has been one of the principal returns of the Voyager mission. And so we had to design the sequence of observations to sort of not to presume we knew what the answer was, but in fact to be broadly based in our exploration. And in fact, that paid off, because time after time we discovered things we hadn't expected to see. And that's because we were smart enough to actually plan a sequence which gave us the opportunity to find what was there. We started building the spacecraft in 1972. We launched in 1977. We got to Jupiter in 1979, 7 years. For 7 years, we were just getting ready. And then for a period of about 10 days, every day you would come in, look at the data, and see what nobody had ever seen before. And you look at that and say, wow. And we knew, though, that the next day we would have even more data, which was even better. And day after day, it was just a flood of discovery, a very exciting scientific experience. You know, the sun creates this huge bubble around itself called the heliosphere. It's filled with the atmosphere of the sun blowing outward at over 1.5 million kilometers per hour. It's a supersonic wind. It creates this huge bubble. Outside the bubble is the wind from the explosion of their stars. This wind from the sun is supersonic, which means that as it approaches contact with the interstellar wind, it has to slow down. And it slows down in a supersonic shock. We expected there would be such a shock because we knew the wind was supersonic and therefore had to go through a shock to slow down. We just didn't know how far away it was from the sun. And so we finally reached that shock back in December of 2004 at a distance 94 times as far from the sun as the Earth is. But that's still inside the bubble. It was not until just 2 years ago that Voyager finally left the bubble and entered interstellar space. Around the sun, maybe 5, 10, 15 million years ago, there were huge, massive stars that had formed, and after a few million years of lifetime, they blow up. and eject all of the stuff they're made of back into the interstellar space. And we are now immersed in that material which was ejected by these exploding stars 5, 10, 15 million years ago. And that's the wind which is out there, is from these explosions. We knew we left the bubble by several different key factors. First of all, we measure the density of the ionized gas inside, which is the solar atmosphere, and outside, which is the interstellar wind. Outside, the density is 40 times what it is inside, and we measured that density and found that in 2012 it became 40 times denser than what had been inside when we were inside. Outside, there are more cosmic rays because they can't get in. We get outside, we see them for the first time, so we're seeing more cosmic rays than we've ever seen before. And we did have some particles inside, and those are gone. So we saw the particles inside disappear, we saw the particles outside appear, and we saw the density go up a factor of 40, all of which told us that we were now in the space between the stars. It now takes almost 18 hours for a signal from the Earth to reach Voyager, and then of course another 18 hours before the Voyager can tell us, yes, I got the signal. I'm often asked, have we left the solar system yet? Has Voyager left the solar system yet? No, it hasn't. It has left the bubble the sun makes around itself, but it has not left the solar system, because outside the bubble, much farther outside, is the Oort cloud of comets, which are comets that are loosely orbiting the sun, so far out that a little bit of a perturbation and they can drop in and be a comet that we see. And so this was a hypothetical cloud. Turns out that it'll be 330 more years before Voyager comes to the inner edge of that cloud, and about 30,000 years before it goes out the other side of the cloud and finally is in a cloud around the nearest other star. And so we are going to be inside that part of the solar system for another 30,000 years. Unfortunately, Voyager will no longer be telling us what it's learning. We have enough electrical power to keep going until about the year 2020. And as the power decays away, we'll have to start turning instruments off one by one. And by 2025, we'll have to turn off our last instrument. And that will be the last time that we will be learning something new from Voyager. But Voyager's mission will continue because it will, in fact, orbit the center of the Milky Way galaxy for billions of years. So this will be Voyager's silent journey. Voyager will become our silent ambassador to the Milky Way galaxy. I think many of us, and I am included in that, hope that someday humans will visit Mars. It's going to be a challenge, and it will take much learning, because Mars is indeed a much longer journey than just going into low Earth orbit or even going to the moon, which is nearby and before we can get back home in a few days. Once you head to Mars, you're on a several-year journey no matter what. And so it'll be very challenging, but I think the human urge of actually being there is such that this will, in fact, eventually be part of our history. I think it's several decades yet. And I think it depends on how rapidly we learn how humans can survive and work in space effectively. We hope someday that we will have samples back from Mars. And the key was we won't have many samples because this would be a challenging thing to do. So the key is to be smart enough to pick the right samples. And that's what's going on now with the current rovers, is they're trying to tell us, where are the interesting places? If you had to pick one place on Mars, where would you pick to get a sample that would teach you the most?
Can you describe what the golden disk is? Who decided what was going to be on the golden disk?
It looks just like an old-fashioned grooved record, and we have included a phonograph cartridge on the spacecraft so that if it should be found, the device to actually play back the record was included. There was a small team headed by Carl Sagan that developed the disk in about 6 months just before launch. I think they did a wonderful job in the 6 months they had trying to capture the essence of Earth. And it's really a tough job to do when you have a limited amount of data that you can, after all, it's there not very much data. Greetings from 50 or 60 different languages from Earth, for instance, and a comparable number of short pieces of music, and about 100 images. So think of trying to characterize the diversity of Earth with so little data. So I think they did a wonderful job. You know, it's unlikely this record will ever be discovered. The Milky Way is immense. But I think more important than actually than somebody receiving the message was this was a statement, basically, that we as a society could actually send a message to the Milky Way galaxy, which will be basically in orbit out there for billions of years.
What motivated you from a personal and a scientific standpoint to get involved with Voyager? What opened your eyes? What were the worlds that became alive for you?
I was a graduate student at the University of Chicago in 1957 when Sputnik was launched. So I was very fortunate to have been right there at the beginning of the space age, and I worked with Professor John Simpson, who was studying cosmic rays, these particles from the galaxy that come in. Some of them can get clear into the Earth, even inside this bubble, but many can't get in. They're kept out by the wind. And so what we had hoped to do was develop an instrument which could be launched and get outside the bubble and for the first time determine what's out there. And that all began basically with my thesis research, which was launched in 1961. And I was fortunate to have been just at the right time to be able to be involved at the beginning of Voyager. We were working on an instrument, designing an instrument that we hoped would fly on what was called the Grand Tour of the giant outer planets. Beginning in 1970, I was here at CALTECH at that time. And in 1972, when they decided to start the mission as a 4-year mission to Saturn only, JPL, which is run by CALTECH for NASA, I was asked if I would go up to JPL as a professor on a part-time basis to serve as the chief scientist for this new mission. And so I decided this sounded like a wonderful opportunity, and that was 1972. And I've been the chief scientist since that time. Well, the thing which really is so important about a mission like Voyager and science in general is you learn new things, and you learn how to do new things, and you learn about new things. And that's what keeps you young, because it means that somehow what you are tomorrow is not what you are today, and you can look forward to a future which is not just a repeat of the past. So I think it's very energizing to be learning something.
Has this fulfilled your wildest expectations?
Way over anything I could have imagined. And there's no doubt that this mission is really, really the amount of discovery from Voyager has just been overwhelming, and so it's been great.
What would you offer to young people today who are interested in science?
You have to, of course, have a systematic approach in order to learn things which are correct. So there is both a systematic part, but there's also the wonder part. That is, nobody knew this before, at least I didn't know this before. Why is it that way? Why doesn't it behave differently? And many people are discovering things all the time, and you can share in their discoveries as long as they're open about what they're doing. So that's another thing we tried to do on Voyager, was as we were exploring, we would have press conferences every day where we brought everybody along with what we knew, what we understood, and what we didn't understand at the time.
Give you an overview of the Voyager mission, highlighting recent analysis, and of course presenting pictures taken of our solar system. To do this, we have Dr. Ed Stone, Voyager project scientist from the California Institute of Technology. Later, we'll have remarks from Dr. Carl Sagan, professor of astronomy and space sciences at Cornell University.
And I think that is even more able to do that these days with the internet, because now everybody around the world can see exactly what we see at the same time we see it. And so I think it's a wonderful opportunity. Voyager was a wonderful opportunity, and space in general is a wonderful opportunity to engage the public in this process of learning, of seeing what's new, of thinking about a future which doesn't just look like what they already know. Voyager, of course, the Voyager science team was roughly 200 people at one time. The science team was organized, there were 11 different investigator teams. One of them was the imaging team, which did not build an instrument, they just used the instrument, the cameras which JPL built. And the radio science team didn't build an instrument, but they used the big antenna, which Voyager needed anyway to do radio science. The other 9 teams each produced an instrument. The team I'm on built the cosmic ray instrument, which was on the spacecraft. So there were 9 of these teams, each of which was in a general area. So the imaging team, of course, looked at the planet and the moons and the rings. The magnetometer measured the magnetic field of the planet, so that team focused on that. So each team had its area of focus, and within each team there were experts in the different disciplines which were part of the analysis interpretation. So I certainly worked with many new colleagues during the planetary encounters, and I've continued, of course, to work with a smaller team now on this new mission, the interstellar mission. But that's introduced me to still other colleagues who are also studying the interstellar mission, but doing it remotely from here on Earth. I can tell you Voyager has been part of our family now for over 40 years. Our daughters grew up with Voyager, and now our grandsons have grown up with Voyager. So it's very much part of what we all think about.
Is it common, do you think, amongst scientists, or is it something that you've experienced, particularly maybe when you were very young and coming into finding your way through science, that one wonders why Earth and why not all the other planets?
In the case of Voyager, of course, we hope to learn how planets form around the sun. And it turns out, of course, today we know there are many other planetary systems around other stars, all of which are quite different than the one we live in. So we don't know how atypical our solar system is, but it's an indication that, in fact, nature has a remarkable diversity in the way it generates and creates objects, planetary objects, and we are just barely beginning to learn the diversity of these other planetary systems. And what we've discovered is that there are many other planetary systems now, hundreds of them, thousands of them nearby, and they're all different, and they're all different than this one. And so I think we are beginning to get the data we need to try to better understand how stars form, and in that process, how the planets orbiting the stars form, and then how those planets evolve in terms of their location. And we now know that planets do not form in the location we see them today. They were in different places and have spread out over time. And it's understanding that process which is critical to understanding life, among other things, because there's only a certain zone from the sun where water is liquid, and therefore life could evolve. At this point in my career, I'm more interested in thinking about how to send robots to other places in the solar system. Robotic exploration is really just humans operating their sensor systems far from home. But in fact, it's all the learning is done by men and women. It's not learned by the robots. It's by all of us who send the robots. So robotic exploration is a human activity. It will be able to go many more places than we ourselves will ever be able to visit, partly because most places are very hostile, and partly because you just cannot afford to go very many places. So the robots will always be on the frontier of exploration. They will go places that no human will ever go, and they will engage us by a sense of form of a virtual presence in these other objects in the solar system. So I think in the long term, it will be an important part of the exploration program. But a virtual presence is not the same as actual presence. And I think there will continue to be a strong interest in actually some few, actually making the trip and coming back from space. Science observes natures in ways that we cannot with our own senses. In a certain sense, the scientific instruments are extensions of our capability, which we have created. So they're really ours, but they're really not part of us. And I think that's what is the power of the robotic program, is not only to take cameras, which can show us what we could see with our eyes if we were there, but to take spectrometers, which can tell us details about the colors and the materials which are there, which we cannot tell with our sensor systems. So we can develop these devices and send them and learn a lot. Both by landing and sampling, which is what's going on Mars today. And eventually, of course, we want to bring samples back, because we will always be able to build better instruments here on Earth than we can possibly send very many places in the solar system.
If you had a blank check, what would be your ideal successor to Voyager? What would you like to do?
I think one of the most exciting problems, that is a very tough problem, is the origin of life. whether life has evolved elsewhere in our solar system or elsewhere in the Milky Way galaxy. And I believe that we will have the capability to learn that. Mars is clearly a spot where we believe there was habitable conditions, and the challenge we have is finding the places where perhaps there's some evidence that life once evolved, maybe some evidence life is still there. There's the moon Enceladus at Jupiter, which has a liquid water ocean, and we know that wherever there's water here on Earth, there's life. Europa today has a liquid water ocean. There may be life in that ocean. And the recent Hubble images show that there are plumes in the south polar region of Europa, suggesting that whatever is in the ocean may, in fact, come to the surface where we could study it. There's the moon Enceladus of Saturn, which has geysers, water geysers erupting from its south polar cap, and again suggesting there may be an opportunity to study stuff which has come from the interior where life might have evolved, microbial life. And there's the moon Titan of Saturn, which has a nitrogen atmosphere like Earth, but no oxygen. It's an atmosphere that may resemble the Earth's atmosphere before life evolved as we know it. The rain in the Titan's atmosphere is not water, as it is here, but it's natural gas, liquid natural gas raining on the surface, forming lakes on the surface of Titan, which then evaporate and form clouds, creating this water, what is on Earth a water cycle, on Titan is a methane cycle. And of course, that may well have been the kind of atmosphere the Earth had before life evolved and created the oxygen in our atmosphere.
Why does man explore?
I think humans explore because they really want to understand the universe, and they want to understand our role in the universe. It gives a new sense of perspective about our role and our destiny, basically, in this universe. It is part of the nature of humans to be curious, to want to understand what is around them, and to try to understand why it's the way it is. And that's what exploration is really about, is exploring and finding what's out there, and then helping collect the information you need to understand why it is the way it is.
How can young people in science find their path?
You know, you can't really design your path. The things I've done, I had no idea I would be doing when I was in high school or even college. And that what you really have to do is to be on a path of learning things, whatever you're doing, look for opportunities to learn things, and then watch for the opportunities where you can go to another frontier where there's something even more interesting to learn. And that's unpredictable. What's predictable is that you need to have learned things to be able to participate in this process. The key thing as a student is to learn the basics and find interesting problems to work on. And step by step, you learn something new and use what you've learned to take advantage of other opportunities as they emerge, because you cannot really predict what the opportunities will be. You just have to be ready for them when they do emerge. Look for the opportunities where the frontiers are. Whatever realm you are in, there are frontiers which have not been seen before. Look for those frontiers, find ways to expand those frontiers, and that's where you'll most likely have exciting things to learn.